Hey there, this is Mr. Alexander. Today you are going to watch 4 videos and take 4 knowledge checks over exponential and logarithmic word problems. This will be the last unit before the test, and hopefully your teacher gave you a blank sheet that has room for a bunch of equations, because in each of these videos I'm going to show you how to use each of these equations. The first one I want to talk about is the exponential growth and decay functions. So yours is blank, but I want you to go ahead and fill it in for me. The first thing I want you to write in is the exponential growth and decay equation, formula, function, whatever you want to call it. It's y equals a times b to the x power. And I want to talk about what each one of those variables means. This y is the value after x periods of time. So if x is years, then this would be, y would be the value after x years. So you've probably guessed that x is a period of time. A is your initial amount, or your starting population, or your starting amount. It's what you begin with. And b is your growth and decay factor, growth or decay factor. So you can write those down real quick, and I want to show you how to use those to solve a few word problems. The first one I want to show you is right here. In the year 2000, the population of Mexico was about 100 million, and it was growing by 1.53% per year. Write an exponential growth function to model this situation. So if we use our little handy dandy cheat sheet here, we know it's going to be in the form of y equals a times b to the x. So that y and that x will always be in the function. The question is, what are a and b? And a is the starting amount. In the year 2000, there was 100 million. So the starting amount is 100 million. That's your a. And it was growing by 1.53%. So I'm going to put my growth factor in parentheses there, and I'm going to raise it to the x power. The question is, what is the growth factor? And generally, what you want to do, I'm going to come back over here to the sheet. To get this growth or decay factor, if it's growing, if it's growth, if it's 1 or greater, or sorry, greater than 1 is growth, and between 0 and 1, that's decay. When x is greater than 1, that's growth. When it's between 0 and 1, that's decay. So we know it's going to be 1 point something because it's growing. The question is what? And the way I like to think about it is that the growth factor is 1 plus the growth rate, which is 1.53, divided by 100. So 1 plus 1.53 divided by 100. So I'm just going to do that in the calculator real quick. 1 plus 1.53 divided by 100. That's what I need to type into the formula, 1.0153. All right, and that's we weren't asked to solve anything. We were just asked to write a formula, which is exactly what we did. Let's apply the same idea to a decay function. So a colony of penguins is currently at a total population of 10,500. The colony is decreasing in population by 14% per year. Write an exponential decay function to model this situation. All right, well, it's decay, but it's still got a y and an x. I'm going to start with y and the starting population, which is 10,500. I'm going to have the decay factor raised to the x power. What I need to type in for the decay factor, if it's decreasing by 14%, I'm not going to add anything to 1. I'm going to subtract from 1 14 over 100. That's going to give me my decay factor. So if it's growth, it's 1 plus. If it's decay, it's 1 minus. So 1 minus 14 over 100 is 0.86. This is 0.86 in here. So whenever the growth factor is greater than 1, it is growing, less than 1, it's decaying. Here we go. The function f of x equals 15,000.863 to the x, where x is in years, models a declining eel population. How many eels will remain in the population after 14 years? Well, this is a simple plug into x question here. So I've got y equals 15,000, the decay factor of 8.863, and after 14 years, so I'm going to raise that to the 14th power. So to type this in the calculator, I'll zoom in on this one. It's going to be 15,000 times 0.863 raised to the 14th power. Looks like there's going to be about 1,906 eels left. We round down because you can't have 0.52 of an eel. So it looks like 1,906 eels. And don't forget to put your units on the answer. That's important. Alright, last thing I want to show you in this video. A lion is introduced into a colony of 20,000 mice during an ecosystem experiment in an attempt to thin the population of the mice. The function below can be used to model the number of mice in the colony after h days. Which value is closest to the amount of time needed for the population of the colony to drop to 14,000? Okay, so I've got a formula, and I want to know how long it takes for the population to drop to 14,000. So I'm going to plug in for y. Instead of having a y here, I'm going to have a 14,000. And I need to get this h by itself. How many days is it going to take? Solve for h. So the first thing we got to do is divide both sides by 20,000. And that's going to give me 0.7 equals 0.752 raised to the h over 4 power. Now, I need to get that h by itself, and I've got an exponential here. At this point, we want to remember our exponent rules. We did this a few days ago. Remember, y equals b to the x, and x equals log b y. So you might write this down on your formula sheet so that you have it handy. I'm just going to convert this exponential equation into a logarithmic equation. So x is, in this case, my exponent, h over 4, equals log base b, the base is 0.752 of the remaining number, 0.7. Well, the h is almost by itself. I've still got this divide by 4. So I'm going to want to multiply both sides by 4. That's going to give me h equals 4 times the log base 0.752 of 0.7. And to type that into the calculator, we have to do the change of base formula. It's going to be 4 times log of 0.7 divided by log of 0.752. So I'm going to type all that in the calculator. Let me show you how to do that. 4 times log of 0.7 divided by log of 0.752. I'm going to hit enter. That's just about 5 days. All right, so that's the end of the first video. Go ahead and try that first knowledge check. Thanks for watching.